Band theory. Okay, band theory is a more comprehensive model for metallic and covalent solids, and this grew out of molecular orbital theory to explain some things that other theories were not explaining. So if we look at an atomic solid, the atomic orbitals of the atoms within that solid combine, like we looked at in molecular orbital theory, and they get delocalized over the entire crystal. When the atoms form these molecular orbitals, the lower energy bonding orbitals get occupied and the higher energy anti-bonding orbitals are not occupied, they're empty. As we get more and more atoms together and they combine their atomic orbitals into molecular orbitals, the energy difference between the bonding and the anti-bonding orbitals becomes smaller and smaller until it becomes really not that important at all. So let's look at an illustration of that. So here is one lithium atom. It has one valence electron in the 1s orbital. When we combine two lithium atoms, they each have that 1s orbital, and those combine in a molecular orbital to form a bonding orbital and an anti-bonding orbital. The anti-bonding is higher, the bonding is lower in energy. If we put in a third lithium atom, now we have three s orbitals combining to form molecular orbitals. And what happens is we get this combination here. So the anti-bonding orbital and the bonding orbitals are there. Here's Li4, and we see here that the bonding and the anti-bonding orbitals here, this one didn't work out very well. These two are closer together than these two. Do you see that? This line and this line are closer together. Because as we add more and more and more, these start to blend together and they get closer together. So what we end up with is a bunch of empty orbitals that are just slightly higher in energy than the occupied orbitals. So these are molecular orbitals, an orbital that is spread out over the entire molecule, the entire solid. The highest occupied molecular orbitals, those are called the valence band. That's where the valence electrons are. The electrons there cannot move. They're stuck because there's electrons next to them. But if they move up in energy just a little bit into the empty antibonding orbitals, that's called the conduction band, then they can move from one end of the substance to the other. Metals have no gap in energy between the valence band and the conduction band. And so because there's no gap in energy, it's very easy for the electrons to move up into that conduction band. It's a little bit like a carpool lane, right, on a congested freeway. And so there's no penalty for going over there, and so electrons can very easily get into the carpool lane and they can just zip down as far as they want. Metals, so that makes metals good electrical conductors. This also explains the thermal conductivity of metals. Those mobile electrons in the conduction band transport thermal energy throughout the crystal. So electrons can also have thermal energy. And by the electrons being able to move around, they transmit or distribute the thermal energy from one side of the metal to the other. So in a conductor such as a metal, there's no gap between the valence band and the conduction band. So here's the jam-packed freeway, and here's the empty carpool lane, and there's no barrier there. All you have to do is move over, and you're good to go. In an insulator, there's a large energy gap here. There's like a grassy median. It's going to be really tough to get across over here to the conduction band. And so insulators do not conduct electricity because it's too hard for those valence electrons to move into the conduction band. There's this big gap. In between, we have semiconductors. Semiconductors have a small energy gap. So it might be like a bumpy curb, you know, those big bumps that they put on the freeway sometimes. And so you can get over them, but it's a little bit annoying. So it takes a little bit of effort to get into this open lane, but they can do it. So semiconductors have limited conductivity. And we can actually tweak them and alter their conductivity, which is what makes them so very useful for computers and other electronic devices. We can control their conductivity by adding other substances to them, and it's called doping. Okay, so the stuff you add is a dopant. So you add stuff to the semiconductor. There's two ways you can increase the conductivity. One is by adding an N-type dopant. So an N-type semiconductor, we're going to add an element that has more valence electrons. So if we take silicon, which is in group 4A, it's got 4 valence electrons, and we dope it with phosphorus. The phosphorus atom has 5 valence electrons. So now we've got some extra electrons in there, and they're not going to fit into the valence band because the valence band is full. And so the extra electron from each phosphorus goes into the conduction band. And those electrons are mobile, and they will carry an electrical charge. In a p-type semiconductor, we do the opposite. We'll dope silicon with 4 valence electrons. We'll dope it with gallium. Gallium only has 3 valence electrons. This creates holes in the valence band. And now the electrons within the valence band can move because there's a hole. So one can move into the hole, and that makes a different hole, and another one can move in. And so the silicon chips inside your cell phone, inside your calculator, inside my computer, have millions of p-n junctions where you have a p-type semiconductor meeting an n-type semiconductor. And these can act as diodes or amplifiers. And if you know what those things are, you'll think this is really cool. And if you don't worry about it. You do need to know what a p-type semiconductor is, what an n-type semiconductor is, and that they're used in silicon chips.